diffusion-based methods, which are very popular and were pioneered in 2015 by Sol Dixtein in this paper. And it has inspired, so many different architectures, so like diffusion models, but of which there's like DDPMs and flow matching. These are extremely popular and also very well working architectures and models to generate data. But beyond the fact that, they work extremely well, I think that diffusion-based models attribute a lot of their success to the fact that they're rooted in physics, for one, and that means that they have a more intuitive way of working. And the way they work, broadly speaking, is as follows. Under our assumption, we have our data that's on a manifold. So here it's on our torus, right? And what you're going to do is you're going to diffuse this data. And what I mean by that is that you're going to convolve your data, that is, let's say, mu, you're going to convolve it with a Gaussian of zero variance and sigma square of zero mean and sigma square variance. So effectively what that does is that it's kind of going to push our data outwards or in every directions, right? And so it's going to blur our data. And we keep blurring and we keep blurring and we keep blurring. And while we're blurring, we're going to teach a neural network to learn something called the score field. And this score field, a way of thinking about what it does is that as you're blurring, you're going to learn the displacement of the data point. So as you're getting noisier and noisier, you're learning how the data points get pushed outwards. And we do this until kind of morally sigma goes to infinity. So what that means is that you've destroyed all your data. It's completely noised and it does not make any more sense. So we would get something like this, where we don't recognize our shape anymore. But we've learned the trajectory. And so now to generate a new data point, we sample a random Gaussian in our Euclidean space, let's say here, and then we push it against the reverse dynamics. What that means is that instead of taking sigma going to infinity, we're going to take sigma from infinity going down to zero. So it's kind of like we're reversing time, right? In one case, you're expanding it, and now you're going to contract it back. And empirically, what happens is that your random sample is actually going to be really close or very well distributed on your data manifold. And this has been kind of the cause of the empirical success for not only image models, but a lot of different kinds of data like text and image-based, and even in science. We use diffusion models all the time.